We've already talked about the gravitational force of attraction between any two masses. So it might be m1 and m2, or it might be a big M and a little m, but they'll be set as a distance apart between their centres, from there to there, and you can call that D or R, varies from book to book, but the force formula there will be the force equals the constant of gravity, universal gravitational constant, times by the mass 1 times by mass 2, and that'll be over d squared or r squared depending on which book you're using. And don't forget, G is a universal constant that works everywhere, 6.67 by 10 to the minus 11. Alright, that's the force of attraction, or the weight of your body on the planet if you use that force formula with the mass of the planet and the mass of your body. But be aware then that any sort of planet has a gravitational force field around it then, where the force field lines are going towards the centre of it and pulls it in. And we need a way of defining that gravitational force field G. And one of the ways of doing it is to say in the lab here you could hang a test mass there of 1 kilogram off a spring balance and measure the amount of force that the mass pulls down with. So you'd actually measure the force per mass. So G by definition is actually the force acting per 1 kilogram test mass that you can use. So that's as a definition there. So if we look at that here, so the gravitational field strength is defined as the amount of force acting per unit test mass that's been placed at that point, and as I said, you could hang a spring balance there to measure the force, and obviously you know the mass. So it's in an example here, if you had a 2 kilogram mass hanging in the lab, you would be using 19.6 newtons of force, so the average is there 9.8 newtons per kilogram. So the average here is 9.8 newtons per kilogram. And if you're looking at that, that is very much the same as the acceleration due to gravity. So the value would always be the same as that for acceleration. Alright, because don't forget that A equals F over M. So this is the acceleration, it's 9.8 meters per second, alright, or meters per second squared, and the gravitational field is also the same, it's 9.8 newtons of force per kilogram. So it'll always be the same number, but they're actually slightly different ideas in terms of what they mean as a definition. Okay. Now if you look at some examples of this then, if you did a test mass all the way around the lab at any height and any way across the lab, the field will actually be uniform. You'd always get 9.8 newtons for every kilogram. So because the uniform field, you can draw vector field lines there to indicate the field strength and the size of the field and the direction. The arrows tell you the direction, and the actual spacing between the lines tells you the size. So the size of the field is the number of lines in a given area. If they're closer together, you'd be finding the field being stronger. These are evenly spaced and they're parallel, okay, and therefore we expect this field must be uniform or even. They're pretty much close to being evenly spaced. So that's a uniform field. If you then go and actually look further away from the lab and actually consider much bigger distances from the Earth, you find that the field lines here are spreading out, and that indicates that as they spread out, the field's getting weaker, and at the surface the field is stronger. So those field lines do give an indication of size and direction by the spacing and the arrows that are there. Okay. Now it's not very easy to work out the field strength here unless you go and hang a test mass there and measure the force on that test mass. So we need another way of finding a field strength around the Earth's surface and away from the Earth's surface, indeed on the Moon, before you send spaceships to the Moon and try and actually take off from there. You need enough fuel to take off based on the amount of gravitational field there is there. So how do you find the field strength without actually going there? Well, there's another way of doing it there. You could go and do a substitution here. So looking at this one here, you could actually substitute, because the field strength there at this point here, G, you could imagine we've hung a test mass there, so we'll just give it a test mass there, call it MT. But the actual gravitational force that's acting on that object would depend on the test mass that's been placed there and the mass of the planet there. So we've got a formula for that attraction, mass of the planet and the test mass, over d squared or r squared. You could substitute this in for force. And if you do that now, you'll find the test mass is no longer important there. You actually come up with a formula that's not based on having a test mass there. We can work it out simply by knowing the source of the field. What is the mass that's producing the field, in this case the planet, and how far away are we interested in it from there to there. So that's a much more useful formula to use, and it's the one we commonly use to find gravitational field strength. So just remember that's the grav field strength we're using this formula to find gravitational field. It's the source, okay, and how far away you are. And if you ask any questions about gravitational force, we're normally using that one there that tells you the force of attraction in newtons between the two of them, or the weight. Okay. If we do one more question here, then we could try this out and actually talk about the Earth for a second and say, let's just check what the field strength here is on the Earth's surface, and it will be G equals G m of the Earth divided by the distance, or the radius of the Earth squared, so how far it is from the centre to the edge. Okay, and we would put in a substitution there of 6.67 by 10 to the minus 11. Mass of the Earth is about 6 by 10 to the 24 over about 6.4 by 10 to the 6 meters, and you would square that and you'll get very close to your 9.8. I think it's about 9.77 newtons per kilogram, and of course we expect that to be about 9.8, the same as the acceleration due to gravity. Now what this formula allows you to do then is actually work out what the field strength is out here, say 3,000 kilometers up. What's it like when we get this far away from the Earth for astronauts? And all you'll be doing there is exactly the same formula, but in here you're going to add on 3,000 kilometers, or 3,000, now kilometers to meters you would times by 10 to the 3 to convert from kilometers. That's the prefix there, and that's the number you'd have to put in and square in there, and you'd find the field strength that was a lot weaker.